our first example was the identity operator on little l2 of z. And that was convolution by this sequence here. And let's again mark the 0 slot with a little box. So what do we have to do now? Well, we know the sequence A that acts here via convolution, and we need the function A upside down hat that acts here via multiplication. So how do we compute A upside down hat? Well, it's the function whose Fourier transform is A. So it's the function that you can write down like this by using your little a's as Fourier coefficients. Okay, nothing easier than that. So you just multiply each entry of your A sequence with the corresponding power of t, and then you add up. But there's only one non-zero entry here, so that gives you 1 times t to the power of 0, because that was position 0. Okay, and if you do the maths, then you get it's 1 times 1, which is 1. So this is a constant function. In particular, it doesn't have any zeros, so the operator must be invertible. It's not that big of a surprise. It's the identity operator. Now let's see what the spectrum of the identity operator is. Well, it's the image of that function when you run it over the whole unit circle. Well, if this is the unit circle in the complex plane, I'm even showing the orientation here, then our function A hat, or upside down hat I should say, is mapping these points all into the same point, which is the point 1 over here. So the image of that function is the set of all images, which is the set of just the point 1, and that's the spectrum. So the spectrum of the identity operator is just the point, the set consisting of just the point 1, and also that is not a big surprise. Well, let's look at the other examples. Maybe they are a bit more substantial. Our second example was the forward shift, and that was the operator of convolution by this sequence, where you have exactly one entry equal to 1, or the others are 0, and this is sitting at position 1. So the function whose Fourier coefficients these are here must be the function that gives you 1 times t to the power 1, because this 1 is sitting at position 1. That's why you write power 1 here, and of course that is just t. So every point of the unit circle is mapped to itself, and hence the whole unit circle is mapped to just itself. Okay, so the new curve is not passing through the origin, so the function has no zeros, operator must be invertible, and the spectrum is just the set of values that I'm painting in red now, which is the unit circle. So we said that before, several times even, but now this is the first time we can actually prove it. Okay, excellent. Next example, number 3, was the backward shift, and that was the operator of convolution by this sequence. So this time the single non-zero and 1 entry is sitting at position -1, so that the function A upside down hat, whose Fourier coefficients you can see here, is now 1 times t to the -1, because this is position -1 here. And because you're on the unit circle, you can simplify, well, is it a simplification or not? I don't know. T inverse into T complex conjugate. And now while T is running around the unit circle, its complex conjugate is also running around the unit circle, but in the other direction. Well, still, the spectrum is the unit circle, which is the image of this function, the set of all outputs. In particular, also the backward shift is invertible. The spectrum doesn't contain 0, or this function, this curve doesn't cross the origin. Example number 4 was the discrete Laplace operator in 1D. And it's the operator of convolution by this sequence here. And the corresponding function A upside down hat is now this here. So you have your coefficient 1 over h squared, and then 1 times t to the power minus 1, because this is position minus 1, minus 2 times t to the power 0, because that's position 0, and 1 times t to the power 1, because that's position 1. And then you again simplify, turn t inverse into t complex conjugate, and recall that the complex number plus its complex conjugate gives you twice the real part. So if we again let t run around the unit circle, then let's first look only at this bracket. What's this doing? Well, we have 2 times the real part. So the real part is just what you see from t projected down to the real axis. 2 times, and then you subtract 2. So you're starting at 0. And then here's your turning point. And then you're going back to 0. And of course everything here is on the real axis. I was just drawing it a little bit offside so you can see what I'm drawing. In particular, you can see that there is a 0. So the operator is not invertible. And of course we should not forget to divide by h squared. So you see that in fact the spectrum is real. We predicted that because the operator is self-adjoint. So this pattern here is symmetric to the black box. And well, the spectrum is entirely on the negative or negative half axis, including point 0. And that's why you often see minus Laplace operator to be studied and not the Laplace, because then the spectrum flips to the other side and you get something that's positive, definite or semi-definite. So let's not forget to write it down. The spectrum of our discrete Laplace operator on 1D is the closed interval from minus 4 over h squared to 0. Okay, we didn't look at example number 5 before, but now let's take a new example, number 5. So let's take the operator of convolution by the following sequence. So the band of this matrix, or the non-zero entries of this sequence, range from position -4 to position 4. So it's clear what the corresponding function a upside down hat is doing. It's -1 times t to the power -4, and then this times t to the -3, this times t to the -2, and so on. And when you apply this to the unit circle, then you will get our lovely fish. So this here is the fish sequence. Convolution by that gives you the operator whose spectrum the blue curve is. So in particular, you see that a upside down hat is a continuous function, which is essentially a deformation of the unit circle into that funny fish curve. Don't worry too much about the little red stars here that look like fish bones. We're going to come to these in a bit. But they are not part of the spectrum. The spectrum is just the blue curve surrounding the fish.